The Muon mystery solved. Why physics' most promising crack may have been an illusion for decades, particle physicists believed they had found a smoking gun. A persistent discrepancy between theory and experiment involving the muon. A heavy, unstable cousin of the electron suggested that the standard model of physics was incomplete. It hinted at the existence of a fifth force, or undiscovered particles lurking in the quantum shadows. However, groundbreaking new research published in Nature suggests that this rule-breaking particle wasn't defying the laws of physics after all. Instead, the anomaly was likely the result of incredibly complex mathematical hurdles that scientists are only now beginning to clear. The Muon anomaly. A 50-year discrepancy. To understand the significance of this finding, one must look at the muon's magnetic moment. In quantum terms, this describes how a muon behaves like a tiny magnet when placed in a magnetic field. According to the standard model, this value should be predictable. However, for over 50 years, experimental measurements from facilities like CERN, Brookhaven National Laboratory, and Fermilab have consistently shown a slight deviation from theoretical predictions. Why this mattered? In physics, even a tiny deviation is a massive signal. If the muon truly behaved differently than predicted, it would mean the standard model-hour current rulebook for the universe was broken, forcing us to rewrite the fundamental laws of nature to include new forces or particles. The culprit, the complexity of the strong force, the reason the discrepancy existed wasn't because the physics was wrong, but because the math was nearly impossible to get right. The primary obstacle is the strong force, the most powerful of the four fundamental forces, which binds quarks together. The strong force is notoriously difficult to calculate because it does not behave linearly. It grows stronger as particles move apart. This complexity creates a noise in the calculations that can easily be mistaken for new physics. A new mathematical approach to solve this, a team led by Zoltan Fodor of Penn State, moved away from traditional methods. Rather than reinterpreting old experimental data, they utilized lattice quantum chromodynamics, LQCD. The method, researchers divided space and time into a microscopic, three-dimensional grid, a lattice. The execution, they used massive computational power to solve standard model equations within these tiny cells. The hybrid strategy. By combining these high-precision lattice calculations with existing experimental data, the team was able to account for the strong force with unprecedented accuracy. Results: a victory for the standard model. The study's results are a masterclass in precision. The new calculations bring theoretical predictions and experimental measurements into alignment within half a standard deviation. We applied a new method to calculate this discrepancy quantity, and we showed that it's not there, says Zoltan Fodor. The old interactions can explain the value completely. While the news is a disappointment for those hoping to announce the discovery of a fifth force, it is a monumental victory for quantum field theory. The findings confirm the accuracy of the standard model to 11 decimal places, proving that our fundamental understanding of how matter and forces interact is remarkably robust. What this means for the future: this discovery does not mean the search for new physics is over, but it does mean the map has changed. One of the most promising leads, the muon's anomalous magnetic moment, has been closed. Scientists must now look elsewhere for cracks in the standard model. While the fifth force may not be hiding in the muon's magnetism, the precision achieved by this study provides a much more stable foundation for all future explorations of the subatomic world. Conclusion: the long-awaited break in the standard model has been revealed as a mathematical error caused by the complexities of the strong force. While the dream of a new fundamental force has faded, the study provides the most precise validation of quantum theory to date.